this is what we're going to talk about. Okay, so we're going to talk about 1.2 today, the spectral collection. From now on, it becomes quite technical. So if you're not sure of anything, feel free to ask. Put your questions in a chat box or in the online system that Anne has prepared. Okay, so don't worry about it if you're not sure what's going on. It took me quite some time to understand. It is a big multidisciplinary project to make this framework happen. So now we look at the spectra. So spectra will mean imaging. We look a lot on the image. Your image, you take pictures on your camera phone, your mobile phone. All these are all pictures. Okay, what we know is RGB. So red, green, blue images. But within RGB pictures are something quite special. Something called spectral, hyperspectral, infrared imaging, and all these things. And I will show you the difference of it. So if this one image, you can help increase data accuracy of your point cloud. Okay, so what we're looking at is point cloud data. At the same time, we're going to combine it with a spectral collection of data. So when we look at the camera, everyone cameras will say 2 megapixel, 3 megapixel, 4 megapixel. What it means, okay? Nowadays, phones up to 7 megapixels. 7 megapixels. What it means actually is 7 million pixels per inch. I repeat, 7 million pixels dots per inch. One of these box represents 1 pixel. So now we are analyzing pixel by pixel. And because each pixel behind a spectral image has a lambda or a microwave behind it, and that's where the information comes from. Okay, so 7 million pixels in your camera. Now we're looking at 1 pixel. Okay, what we do is in your RGB, you only get the purple in color ones. What we want to check is also on the lambda side, so you go across the spectral and also diagonally. So don't worry about that. It's just give you a visual representation of each pixel manipulation that we need to create. So what we have is this. The scene is the picture of the flowers. We have this hyperspectral imaging system, and this is spectral imaging towards the different microwave we have, okay, from 400 to 720. A hyperspectral imaging system like these costs about £20,000. It's expensive, and the limitations of a spectral imaging system is that it needs to be done in a very controlled environment, meaning in labs. So for buildings, fine, we can do it still in a nice sunny day. We can still do it because of imaging systems. When there's a different light, you get different images coming up. So this is on the imaging side. Okay. So for example, this is the picture. We are looking at 1 pixel. Will look something like this. Okay, 1 pixel right there. This is the spectral image. And this is around here. This is what we know. The color bar at the bottom is what we see in your Microsoft Office when you choose the color of your font, for example. So this is the standard RGB, and it belongs right there. It's a purple. It looks like this, and that's how the spectra. And the leaves is right here. This is how it looks like. So different colors provide different wavelengths. Okay, and each wavelength tells us different things. So the advantages of it is that we can extract both the spectral and the spatial properties together in high resolution. It is non-destructive. I repeat this very importantly, is that all these pictures taken is non-destructive. There is another technology in laser whereby a laser can be shot at an item, and then what it does, it can compile a very accurate material information, but you scratch the surface of the item. So obviously in heritage paintings, we can't do that. That's why imaging is so popular within the heritage side of it. Okay, so the historians love images. I'll give you examples later on. And then on the disadvantage side is that you need a spectral imaging range. So basically, you must create your own database of it. It's quite time consuming to create this database. There's also depending on the environment, as I said. So imaging, the lighting that's the biggest problem we have at the moment. Okay, so spectral data collection is not perfect. It's up and down, but at the moment, this is the best way forward. So this for one example that one of my students did project for the library. You can see this is a very old Hebrew manuscript done in the 14th century. So when we take a picture of this, you can see the blue, it looks like this. You can see the text now is that wavelength. But what we don't know is you can look at the dirt, at the stain at the bottom right corner. Is the stain part of the text? That's all what I want to know. Okay? So when we take the picture of it, the stain has a different wavelength. So now we know that this part at the bottom right here is not part of the manuscript, but it's a stain. Because why? The spectra image shows a different curvature altogether itself. So again, this is point by point pixel manipulation. Okay. And then when we look at the construction side of it, when we look at work as some other researchers have done, this is the wavelength. So as I said, we've done previously is 400 to 700. Now, what this researcher is taking much further. The wavelength now is up to 2,350, and this camera costs a lot of money, okay, to get these kind of results. So if we do the more conventional way, as you can recognize asbestos is quite clear, the difference of it. So new asbestos, old asbestos, we can identify. Now look at the concrete. We cannot really identify much on the concrete side, okay? It's a little difference into it, new and old concrete. And now you look at the clay, it's very close together. So this pixel by pixel will give us information of every materials that we want. That's great. At the same time, we also can recognize whether it's a new product or the old product, and that's what we really want. Okay, through this research, these researchers managed to come up with the structural damage of the building. So where has been repaired, what's not been repaired, so on and so forth. In the building side of it, we can also detect asbestos, and that's what we want. Okay, so the wavelength of it, we are able to detect the type of materials already. However, there's a problem of it. When we do point cloud data, like we done this scanning of the little guy right here, we can take a picture of the imaging. However, when we try to paste the picture, we are missing a big chunk of it. What's behind the statue, we cannot paste. And this is a big problem. So within scanning, within some imaging, there are some parts that we cannot get data of. Okay, so for example, things that we cannot scan, what is behind the object, we cannot scan, there's no data of it, and that's a problem within the spectrum. Okay, so once we get a spectral data, we clean the data all together. Okay, and then now we try to combine them together. That's what we want to do. We need to combine it together. So imagine you have your point cloud data, and now you try to wrap it up with your picture. Imagine that way. Okay, this is one example. One of another research is done. So this is a building picture, and this is the edge detection. So basically, what we're trying to do is that now we can recognize that these squares at the top are windows. Now we know that the computer doesn't know. We know, as humans, we know. Okay, we can now start edge detection and separate the windows and the bricks, so on and so forth. For example, in a 2D image that we have, we can start to separate up the picture into different parts of it, okay? And this is done very easily via the computer. So for example, on this table, you get the picture, and then you can start drawing the edges of it. The edges are important. Now we can start to separate to what we want. That's how we're going to help with the point cloud going to help us here. Okay, so once we done the spectral, once we done the edging, now we got a spectra to tell us the difference in materials. Okay, so we combine the edge detection right here together with the different materials of it. Now, the computer will be able to, number one, split up the point clouds. At the same time, now we can put materials information inside the model. Okay. So again, there's a lot of data available out there from quartz, stone, cement, metals, so on and so forth. There's a lot of information out there. Okay, you can use all these, put in there. Once we have the edge detection being done, we can have the spectra being done, and then now is to verify them and make them into objects, BIM objects. That's what we want. Okay, so once we got the individual objects, we need to verify them. make sure that it's the right format, all your standards ISO, your past standards come in, and we combine all the objects into a single BIM model. Now with the multiple BIM objects, again, we put it up there, we combine it up together. So now, once we finish this process, it's a very simple process I could show, but in practice it's quite difficult. We need to verify them, okay? So each object's now combined into a wider BIM model itself. Once we've done the BIM model, is now we start to do the design simulation. And that's where the benefits of your BIM starts, okay? As I said very early on in the UK, is that we need to spend less time on site. We need to make all decisions off site, so that when we are on site, we just fix it correctly, do it well, and we're off. We can save lots of money. All right. So what we can do, two parts. One you can do is to put the design into a environmental schemes, and you go score credits. Okay. So in the design simulation, for example, in Bream or Lotus, for example, we can put the model inside the schemes, and we can see the scores. Once we get the scores, we can start to change things right now. All right. Because a lot of buildings these days in Europe is that we need BREEAM, we need LEED. If not, we cannot build a new building, and that's a problem. And if you can put it within this into the Scan-to-BIM process, why not? Let's do it that way. Okay. This is what we talk about the material information. This is what is missing all the time, whereby we always assume that timber is zero carbon. It is true, timber is zero carbon when you start to use the timber, okay? But it consumes a lot of energy to grow the tree, but no one's calculating the growth of the carbon in the tree itself. All right, what we want to know is all these things, okay? We need to calculate the embodied energy of the construction and building products. Embodied energy, as I said very early on, is the process of start to finish. I'll explain. Embodied energy, what we have is something called EPD, Environmental Product Declaration. It's a standard past 2050. I can distribute later on. Basically, it calculates energy and emissions from raw material extraction, transport, assembly, all the way to decomposition, basically end of life, really end of life. All right. When we look at what we do at the moment right now, we only look within the in use B1 to B7. Part A is not considered at all. All right. And part C, forget it. No one is doing part C. So what we are looking now at the moment in the UK is very strongly between part A1 to A3. We can calculate easily A4 to B7, no problem. So EPD allows us to calculate the whole life cycle of every individual building material, okay? And this is what we call embodied energy. At the moment, as I said, what's being calculated is B1 to B7. That's all. And B1 to B7 in use is only 30% of the whole life of the material. What we look at, we need the more of the 70% of the whole process. It's not being calculated for, okay? This is one example. So Dorma is a system for sliding doors. It's only one system, and now it provides us information from A1 to D. What we look at here, A1 to D on this side is demolished totally, and then what are the carbon emissions of it? It's all information. So there are people doing these things, but it is not enough for a building. In a building, there are thousands of products. I think at the moment we only have about hundreds of products with this information inside. Okay, so a lot of research now is being done into carbon emissions and embodied energy. A lot of people are looking at it at the moment. So once we have all this all together, we can look at the whole life cycle assessment of the building itself. So I keep telling everyone is that Scan-to-BIM is not only the process of it. What we're doing at the moment right now is very, very low maturity. We scan, okay, and then we model. It looks nice in 3D, done. We leave it alone. That's very low to me. That's what is being done at the moment. What I'm looking at right now is towards the whole process. Is that I want to scan, I want to model, great. I want to make it into a BIM model with information inside. I want to do simulation, and now I want to know the bigger picture of the building. So what can I do with it? Okay, in the UK, 70% of future construction projects will be in refurbishment, retrofit, and all these things. There's no more new builds in Europe anymore. No more. I know in developing countries, in Vietnam, Cambodia, Laos, you will have a lot of new buildings, but in Europe is no more now. So we moved on from that, okay? Because we cannot demolish. So the novelty of this research is the integration of laser scanning, imaging, BIM, and sustainability assessments into it, okay? What we talk in part one is the integration of laser scanning and modeling. That's it. So this goes way further. We want to support the creation of the models and storage visualization for retrofit refurbishment of buildings. That's what we're looking at the moment. For developing countries, this should be focused on your very prized heritage buildings. Okay, there's a lot in Southeast Asia that you can do to maintain the kind of a building. Maintaining and retrofitting a building is more expensive than building a new one. At least the case in Europe. Okay, it is always said that it is 50% more expensive than doing a new build. That's why refurbishment is not a popular topic in the UK. It's hard to do. The key thing, another thing of this, you can predict the sustainability performance of the refurb building. Okay, we can tell our client is that if you spend X millions on a building, we can get you to this part of BREEAM, guaranteed. That's what they want. At the moment, refurbishment in the UK is still very hard to predict. Okay, it's all very high risk, and also this process can enable very well-informed decision-making process. Okay, contractors can decide on the options and choices they want to do very early on through the simulation process. However, there are limitations. Okay, it is not a perfect system. That's why it's not out there in the public realm at the moment. It's not done in practice so much because the data is very, very rich. It is complex. So when we discuss about hyperspectral imaging, we are doing pixel by pixel manipulation. And when you have images of 2 million pixels, 2 million pixels per inch, there's a lot of computational strength being needed, and we don't have that at the moment. So last point, high demands in computational power and data storage. It's very hard to do all these things. So you got your point clouds, the gigabytes of data, and now you got your spectral imaging data. Again, it's gigabytes. So we need to process all these things all together. Not done at the moment. We are currently doing some prototyping on my office. Again, it takes a long time, so we'll see how it goes. There's also a lot of unknown materials out there. The data sets are not perfect. Again, there's unknown materials. What we put it in there, especially when we look at very old buildings, there are materials that we don't know of. Limestones, for example, there's a lot of time limestones, the concrete, various other materials out there we don't know of. This is something we need to do research on as well. Okay. Construction and building materials from regions will be different, culturally will be different. Heritage buildings will give it a different challenge altogether because no one has done this before. Okay, so the novelty of this is there. So the push towards the developing countries, Vietnam, Laos, is that this is for your heritage buildings. I keep repeat is that when the heritage is gone, it's gone. You got to preserve it right now. Okay, so this brings to an end of a future thinking approach towards what Scan-to-BIM is. I know it's a bit off the scale, but I think when it comes to the right moment, we will be able to use this technology to information and do the simulation of the whole process. Okay, all right. Thank you very much. So I'm open to questions for now. I'm trying to see, is there any questions? Anybody? Is there any questions, anyone? Current off-the-shelf 3D modeling technologies. I mean, there's a lot out there, but there's a big difference between the scanning part of it, scan to model, or you do it just for the modeling. It's a big difference. So when you look at the structural elemental for new builds, for example, you go to the more popular systems, like the Revit ones, the Autodesk products. At the same time, I know very popular is Tekla. Tekla has a lot of structure into it as well. So it all depends on what you want to do. A lot of times that these softwares are driven by the company itself on what they like to use it for. Okay, But most importantly, of any 3D modeling technologies, you got to make sure it is interoperable. Meaning says that it is shareable throughout. So make sure it is IFC compatible. That is the main thing. Because if it is not IFC compatible, then you're stuck. You are creating in an island. No one can use your data. There's no point. If you can create elements that you can be shared, great. If not, no one can use whatever you created, and that's a problem. All right, second one is do you have any articles / technical reports or other materials to take this topic, review 3D modeling technologies into account and you can share with us? So, yeah. All right, there's a few technical reports on 3D modeling technologies. There's a lot out there. I mean, if you look at 3D modeling by itself, there's a lot of software out there. Even SketchUp, Google SketchUp is a good 3D modeling technology. It depends on what you want to do with the modeling. Are you looking at the larger stuff like the buildings and structures, bridges? If you look at all the big ones, it's always Autodesk products. You can use it. If you look at the smaller ones, you look at things like ANSYS. There's another one, SolidWorks. They do for the smaller ones. So if you look at smaller products, for example, we go towards the mechanical engineering side of it, whereby they can produce even more details. Okay. One of the biggest problems within mechanical engineering is to create the screw threads in each of the nuts and bolts. So that is one of the first projects we ask our students to do within my university. So in year one students, we ask the students to do the threading and the bolts. And then what they do, they can design it. They design it in SolidWorks. And SolidWorks, they need to model it, and then they make it to print. Okay. When they do after printing in 3D model, if it works, great. If it doesn't work, redraw it again. And now we're making them combine it with our electrical students. So electrical students will design it in another software. Again, this software is compatible with its IFC, and we make them all share stuff together. I think interoperability of the 3D modeling technologies is more important than anything else. Okay. All right. I'll move on to the next one. Next question is, in my opinion, what elements should we use to evaluate the productivity and quality of this Scan-to-BIM process? Any suggestion? All right. Okay. This is going to be hard. Number one, it is always accuracy. If we get the Scan-to-BIM model wrong, there's no point going it. So number one to me is accuracy. Okay. So when we scan to BIM, once you got the completed model, how are you going to verify that model? That's the key thing. If you can't verify it, there's no point, because there'll be mistakes, and mistakes will give you more problems later on in that. It also depends on the type of buildings, on type of things that you scan. Obviously, scanning a building is a bit easier compared to a factory, but nonetheless, factories, for piping systems, there's a different software for it, so they might be quite quick. So it all depends on it. So in my opinion, the most important element of it is the quality of it. It must be accurate. Okay, that's the only thing. Be accurate. If it's not accurate, Scan-to-BIM is not helping you at all. So the scanning process must be robust. You are getting the right scans. If you do not have the stitching software, you got to get it right, and that's the biggest problem in the past. I know Leica Geosystem software, the new one, has auto stitching. It saves a lot of problem. But for other softwares, I'm not sure Faro has it or not. The stitching process is the longest and the most not accurate process that we have at the moment. Okay? Yes, it's my opinion. Thank you. Okay. All right.